Hi everyone, this is Professor Muldrow, and it appears that my lecture on this topic, which was from March 24th, didn't get recorded properly, which is probably my fault for not hitting the record button when I was supposed to. Okay, well, I won't go over everything that I did that day, but I will try to give you the basics of how to convert a MIPS instruction into its hex equivalent. The first example I'll show you is for an R format instruction. R format means you've got 3 registers. R stands for register format. So here's what you do. Suppose your instruction is this: add T5, then S3, then S5. T5 is your destination, and S3 and S5 are your sources, first and second. As you can see up here on this on the MIPS handout here on your left as you're looking at the screen, as you can see, for add, the opcode is a 0. Well, I put the word math in there just in general. There's nothing special about the word math. I just did that because that's the opcode for add and sub that we're going to use. What you want to do in the first line of the table is put the registers in correctly. However, you must be aware that it's the source registers that go first in the order in which they're in. So S3 is the first source register. So you put $S3 in the RS box. The RT box gets the second source, that's $S5, and the destination is T5. That is going to go last. Okay. Now then, that's the first line of the table, is to put the registers in. The second line of the table is to put all the decimal values in. The opcode goes first, and for an add or for a sub, the opcode is 0. So a 0 goes there. Now you must use the ID numbers of the registers. It says here on the MIPS handout, S0 to S7 are numbered 16 to 23. So if S0 gets 16, that means S1 gets 17, S2 gets 18, and S3 gets a 19. There we are. And therefore, let's see, S3 gets 19, so S5, that's 2 more, that'll get a 21. And then since destination is T5, well, let's see, if the T's are numbered from T0 to T7, numbered 8 through 15, T7 is a 15, so going back 1, T6 is a 14, T5 is a 13. Now, for an R format instruction, not only does each instruction have its own opcode, it has its own function code. Add and sub, as you can see here, have the same opcode of 0, but their function codes, as you can see on the right, are different. Add has a function code of 32, sub has one of 34. So since this instruction is add, I'll put 32 right there. And then that takes care of everything in the decimal. Now you've got to convert everything to binary. Please recall that the opcode and the function code are given 6 bits. So that means that this 0 for the opcode needs to be replaced by 6 zeros. All right? Now then, the registers all get 5 bits. So that means for 19, well, let's see, that leftmost bit would be equivalent to 16, so that's 16 plus 3. So 16 is in, 8 is out, 4 is out, 2 is in, and 1 is in, because it's 16, 8, 4, plus 2 plus 1. For 21, it's 16 plus 5, so 16, no 8, but 4 is in, 2 is out, 1 is in. 16 plus 4 plus 1 is 21. 13, well, that's less than 16, so your first bit is 0. And then 13 is 8 plus 4 plus 1. So 8 and 4 are in, 2 is out, 1 is in. And finally, the function code, that's 32. So that means okay, that's 6 bits. The function code also gets 6 bits, just like the opcode does. So that's 1, 0, 0, 0, 0, 0. 32, 16, 8, 4, 2, 1. And 32 is the only one with a 1 in it. Okay, so there you have your binary representation. Now, what you want to do is, you want to start to get the hex representation. You could start from either the left or the right, doesn't matter which, and count off every 4 bits and get the hex equivalent number. The first 4 bits here are zeros, so that gives you a 0. So it's 0, 0, 0, 0. Then 0, 0, 1, 0, 8, 4, 2. Okay. Then you have 0, 1, 1, 1. That's a 7. 0, 1, 0, 1, that becomes 5. 0, 1, 1, 0, that's a 6. 1, 0, 0, 0, that's an 8. 0, 0, 1, 0, that is a 2. Then you got 4 zeros on the end. That's 0. So again, to get the hex, after you get the binary representation done, to get the hex representation, you have to start at the left or the right and just count every 4 bits and turn every 4 bits into its equivalent hex digit. And some come up numbers and some don't. Now, here's where it gets interesting. For an I format instruction, that's add I, load word, or store word, well, same thing happens. Let's do load word here. So first off, you got to put the source register. Well, guess what? For load word, add I, and store word, you flip-flop the registers. So since S1 is the second register listed for load word, you put an S1 here in RS. And that means T6 goes here. And then for constant address, well, you take whatever the constant number is. All 3 of these, add I, load word, and store word, have constant numbers. In this case, for the load word, the constant number is an 8. So an 8 goes in there. Okay, you got the registers in. Now it's time to go all decimal. Well, according to the MIPS handout, a load word has an opcode of 35. So we'll put a 35 there. S1, let's see, S0 gets a 16, so that means S1 gets a 17. T6, let's see, T7 gets 15 according to this sheet, so that means T6, go back one, that's a 14, and the 8 is still an 8. There is no function code for an I format, so add I, load word, and store word are all I format instructions. They all have opcodes, they do not have function codes. Okay, so now we got to go binary. Again, the opcode is 6 bits. That's 35. Well, that means the first bit is 32. And this would be 32 plus 3, which means 32 plus 2 plus 1. Well, 32's in, but 16's out, 8's out, 4's out, 2 is in, and 1 is in. 32, plus 2 is 34, plus 1 is 35. The registers still get 5 bits. So we got 17. That's a number bigger than or equal to 16, so there's a 1 up there. 8, 4, 2, and 1. That's 17 in 5 bits. 14, that's less than 16, so I mean a 0 leads off. And that's 8 plus 4, which is 12, plus 2, which is 14. So 8, 4, and 2 get 1s, and then a 0 on the end. And then the constant number in an I format is 16 bits. This whole field here for the constant slash address, whatever it is 16 bits. So we have to convert decimal 8 to 16 bits. So that's 0, 0, 0, 0, 0, 0, 0, 0, 0, and then there's an 8 right there on the end. That is the binary version of this instruction. Now we have to convert it to hex. So once again, I'll start from the left and count off every 4 bits. 1, 0, 0, 0, that's an 8. 1, 1, 1, 0, that's 8, 4, 2, that's 14. Okay, that's an E. 1, 0, okay. Let's see, then 0, 0, 1, 0, that would be a 2. 1, 1, 1, 0, that's another E. Now look, you get 4 zeros, that's a 0. 4 zeros, a 0 again. 4 zeros, 1 more 0, and then a 1, 0, 0, 0, that's an 8. So there's the hex equivalent of that load word instruction. For a store word, guess what? Even though in some way store word breaks the rules, just like you flip-flop the registers for load word for these representations, you flip-flop them again for store word. So that means the S5 goes first. So $S5, and then $T1, and then our constant is a 24, because that's the constant number here. Store word, according to the MIPS handout, the opcode is a 43. Okay, then S5, let's see, S7 gets 23, which means S6 gets 22, so S5 is 21. T0 is 8, that means T1 gets a 9, and then the 24 is still a 24. There's the decimal. Now we got to go binary. Well, 43 is 32, so plus 11, so let's lead off with 32. 11 is 8 plus 2 plus 1, so 32's in, 16's out, 8's in, 4's out, 2's in, and 1's in. 32, 16's out, plus 8 is 40, 4's out, plus 2 is 42, plus 1 is 43. Got it. Okay, 21 is 16 plus 5. 16's in, 5 bits for the registers. 8's out, 4's in, 2's out, 1's in. 16 plus 4 plus 1, that's 21. 9 is less than 16, so the 0 is in front. 16's out. And 8's in, that's 8 plus 1. So 8's in, 4's out, 2's out, 1's in. So there's 9. And then 24, we got to go 16 bits. Let's see. I think that means the first 8 bits are definitely all zeros. Now 24 is less than 32, so it means we're going to have at least 5 bits involved here. So let's see, 0, 0, 0. That means I think that bit's 0, but then you get a 1 for the 16. Then it's 16 plus 8, so 1, 0, 0, 0. That's it. Okay. Because 1, 2, if you start from the right, from that rightmost 0, 1, 2, and 4 are all out. Then you got 8 and then 16. That's 24. Okay. So there is your binary representation. And now we'll start from the left and count off again. So 1, 0, 1, 0. That's 8 plus 2, which is 10. That's A. Then 1, 1, 1, 0. Well, 8, 4, and 2 is 14. That's an E. 1, 0. Okay, then 1, 0, 1, 0. 8 and 2. That's an A again. And then 1, 0, 0, 1. That's a 9. And then 4 zeros is 0. 4 zeros again is 0. 0, 0, 0, 1 is a 1. And then 1, 0, 0, 0 is an 8. Whoops. 8. There you have your representations for load word and store word. I apologize for the previous recording not working correctly. I sincerely hope this helps clear a few things up. If you have any further questions, please send me an email at kmuldrow@lbcc.edu.